You know that moment when you're waiting for ChatGPT to respond and you can almost hear the money burning? Well, LLM inference costs are dropping by 10x every year. But we're still talking about a 30-40 gas station scenario where one provider charges $4 and another charges $40 for the exact same computational fuel.
And here's the fascinating part. The majority of wall clock time during inference is spent in a memory-bound phase, not compute-bound. We're essentially sitting around waiting for data to move rather than actual thinking to happen.
Right. So the big question is, what if most of the thinking happening in these massive models is actually unnecessary? What if we could identify which neurons matter and just turn off the rest?
That's precisely what Microsoft's new Winner framework tackles. But here's where it gets counterintuitive. Every previous attempt at this problem has been looking at the wrong signal entirely.
Today on The Recursive, we're diving into this breakthrough that's not just incrementally better, it's addressing a fundamental blind spot that everyone else missed. We'll explore why existing methods like TEAL rely solely on hidden state magnitudes and how Wina's insight about weight matrices changes everything. Let's start with the problem space. Digit, when you're running inference on a 7 billion parameter model, what's actually happening under the hood?
Picture this. Every single time you send a prompt to an LLM, every layer and every neuron activates in sequence, causing billions of parameter interactions. Research shows that only a fraction of neurons contribute significant information to the final answer. We're essentially running a massive factory at full capacity when we only need a few assembly lines.
And this has real consequences. We're talking about computational power demands doubling every 100 days. But here's what blew my mind. There's already a solution to this called sparse activation, right?
Exactly. The concept is beautifully simple. Identify the most important neurons during inference and just zero out the rest. TEAL, which was state-of-the-art, achieves 40–50% model-wide activation sparsity with minimal degradation, allowing 1.53 to 1.8x wall clock speedups.
That sounds amazing. So what's the problem?
Here's where the story gets interesting. Most existing methods rely solely on measuring hidden state magnitudes and neglect how weight magnitudes shape error flow through the model. Think of it like this. Imagine you're a hiring manager and you're only looking at how enthusiastic candidates are in interviews, completely ignoring whether they have the skills that actually matter for the job.
Oh, that's a brilliant analogy. So these methods are essentially saying this neuron is firing strongly without asking, but does its output actually influence what happens next?
Precisely. And this creates a cascade of problems. You might be keeping neurons that are screaming loudly but producing irrelevant outputs, while discarding quieter neurons that, when combined with their weight connections, actually drive the model's decisions.
Okay, so here's where Wina comes in, with what seems like an obvious insight in hindsight. Tell me about this breakthrough.
Wina introduces a deceptively simple but profound change. Instead of just looking at hidden state magnitudes, it jointly considers both hidden state magnitudes and the column-wise L2 norms of weight matrices. The mathematical insight is that this combination directly reflects how much each activation can influence the next layer.
Wait, let me make sure I understand this. It's not just how loud is this neuron, but how loud is this neuron and how much does the network care about what it's saying?
Exactly. And here's the theoretical elegance. This approach provides formal guarantees that the total approximation error remains bounded and is lower than comparable approaches. They prove this works for both single layers and multi-layer architectures.
The results are pretty stunning. On Quen 2.57b with 65% sparse activation, Wina outperformed TEAL by 2.94% in average performance. But I'm curious about the practical implementation. How do you actually make this work in real models?
This is where it gets technically fascinating. The theoretical analysis assumes something called column-wise orthogonality in weight matrices, essentially that the weight columns are perpendicular to each other. But real LLMs don't satisfy this assumption.
Ah, the classic theory meets reality problem.
Right. So they developed what they call a tensor transformation protocol. They use singular value decomposition to enforce column-wise orthogonality by multiplying weight matrices by orthogonal matrices, while maintaining computational invariance, so the model's final output remains unchanged.
That's genuinely clever. They're essentially reshaping the model's internal representations to match their theoretical framework without changing what the model actually computes. Let's zoom out and talk about what this means. The practical results are compelling across the board, up to 63.7% reduction in floating point operations on Llama 2.7b and 62.7 on 5.14b.
And here's what I find most significant. This is completely training-free. It provides a reliable, plug-and-play avenue for reducing inference costs without modifying original weights or adding training overhead. Compare that to mixture of experts approaches that require extensive retraining.
Speaking of MOE, how does this relate to what we see in models like GPT-4 or Mixtral?
Great question. Mo frameworks require extensive extra training so the gating network can learn expert selection for each input. Wina achieves similar sparsity benefits but can be applied to any existing model immediately. It's like the difference between redesigning your entire factory versus just optimizing which machines you turn on.
The broader implications are fascinating. If inference costs are already dropping 10x per year, techniques like Wina could accelerate that trend even further. We might be looking at a world where running sophisticated AI becomes truly commoditized.
And there's a compounding effect here. TEAL is compatible with weight quantization, enabling further efficiency gains, and Wina shows similar compatibility. You can stack these optimizations, sparse activation, quantization, better hardware, algorithmic improvements.
I'm also thinking about the edge computing implications. If you can cut compute requirements by 60 plus without retraining, suddenly you can run much more sophisticated models on mobile devices, in cars, in IoT devices.
Absolutely. And here's a crucial point. Wina maintains better performance as sparsity increases, highlighting its robustness. Most optimization techniques hit a wall where additional efficiency comes with severe accuracy costs. Wina seems to push that wall much further out.
So let's distill this down. We started with a problem that everyone thought was solved: how to identify important neurons during inference. But the solution everyone was using was fundamentally incomplete.
The breakthrough insight is beautifully simple. You can't evaluate the importance of a neuron's activation without considering how the network processes that activation. By jointly considering hidden state magnitudes and weight matrix norms, Wina directly reflects how much each activation influences the next layer.
And the practical impact is immediate and substantial. Better performance, massive compute savings, no retraining required. It's the kind of advancement that doesn't just improve the current paradigm, it makes entirely new applications feasible.
What excites me most is that this represents a shift in how we think about model optimization. Instead of just making models more efficient, we're getting better at identifying what's truly essential. That has implications far beyond just saving compute costs.
For anyone running AI applications in production, Wina is available on GitHub and appears to be production ready. But perhaps more importantly, it demonstrates that even in fast-moving fields like AI, there are still fundamental insights waiting to be discovered.
Sometimes the most powerful advances come from questioning assumptions that everyone takes for granted. Wina asked, "What if we've been looking at the wrong signal this entire time?" And the answer was transformative.
That's a wrap for today's episode of The Recursive. Remember, efficiency isn't just about doing the same thing faster. Sometimes it's about realizing you don't need to do everything in the first place.